Hello everyone, welcome to Alfonso Academy. I'm Sir Peter Alfonso and we are into the fourth part of chapter Gravitation. So in the starting part we had discussed about the Earth's gravitational pull which acts from the center of the Earth. That means center of mass of Earth is the center of the Earth. So whenever we throw an object up, it returns back down, vertically downwards, and it travels towards the center of the Earth. But what exactly happens with the object? So whenever we throw an object up, it goes up with certain velocity. But that velocity goes on decreasing. It goes on decreasing and at a certain height it becomes zero. And that is the point of maximum height. And the object returns vertically downwards after that. And that is because of the continuous constant pull of the Earth from its center. So the gravitational force is acting as the object is going up and its velocity goes on decreasing, and after certain time at a certain height the velocity becomes zero, and then only gravitational force acts on the object, and that is why it falls down vertically downwards. It travels towards the center of the Earth. Now this gravitational pull acts on every object near to the surface of the Earth. So we have two solved examples on our textbook. The first example, calculate the gravitational force due to the Earth on Mahindra in the earlier example. So we had solved some examples of Mahindra and Virat. So here we are excluding Virat and taking only Mahindra, and we are told to find the gravitational force which acts on Mahindra because of Earth. So the two objects we have to consider is Earth and Mahindra. So M1 we are taking as the mass of the Earth, which is 6 into 10 raised to 24 kg. M2 we are taking as mass of Mahindra, which is 75 kg. And the distance between the two, between Mahindra and center of Earth, because gravitational force acts from the center of the Earth to Mahindra. So that will be your small d, which is taken as capital R in this case, because it is nothing but radius of the Earth, which is 6.4 into 10 raised to 6 meter, and of course the universal gravitational constant, which is 6.67 into 10 raised to minus 11, and the units Newton meter square per kg square. So this is the formula for gravitational force, F equal to G m1 m2 divided by r square. We have to substitute the values and then find the answer for this. So in order to make multiplication easy, I have shown it here. See, 6.67 into 6. We can multiply this first. We are getting answer as 40.02 for this. 6.67 into 6. 40.02. And this 40.02 then we can multiply with this 75. So for that we are getting as answer as 3001.50. So 3001.5 that we are taking in the numerator, and rest of the things we are multiplying separately. So 6.4, this becomes 6.4 square. 6.4 into 6.4, we are getting it as 40.96. So 40.96 in the denominator. And now the remaining things, 10 raised to minus 11, 10 raised to 24, and in the denominator 10 raised to 6 square. So that will become 10 raised to 12. And then this 10 raised to 12 when taken in the numerator, it will change the sign of the power. So it will become 10 raised to negative 12. 10 raised to negative 12. So these three numbers we are taking it separately over here. 10 raised to minus 11, 10 raised to 24, and this 10 raised to 6 square, which is 10 raised to minus 12 in the numerator. So this minus 11, this minus 12 becomes minus 23. And then 24 minus 23. It becomes 10 raised to 1. So multiply by 10 raised to 1. 10 raised to 1 is nothing but 10. So this 10 we can multiply this over here. So 30,015 in the numerator and 40.96 in the denominator, and the units for force, Newton. So in order to remove this decimal, we can multiply and divide by 100, because there are two numbers after the decimal. So 100. Multiply and divide by 100. So we are getting it as 30,01,500 divided by 4096. So that division I have shown over here. So 4096 into 7 we are getting as 28,672, and then this is the remainder 13,430, and then again 4096 multiplied by 3 is 12,288, and then this is the remainder 11,420. These two multiplications I have shown over here, 4096 into 7, is equal to 28,672, and then 4096 into 3 is 12,288, and then this is the remainder 11,420. Then 4096 multiplied by 2 is 8,192. So 4,000 plus 4,000 is 8,000, and 96 plus 96 is 192. So 8,192, and then this is the remainder 32,280. Again we are getting it as 4096 multiplied by 7, 28,672, and this we are considering it as final remainder. So this is the answer for this division 732.7. So this is the answer for the gravitational force which acts on Mahindra because of Earth, and it acts from the center of the Earth. Now this all the calculation seems to be very easy, but you need good practice for this, otherwise you tend to make mistakes in multiplication, division. So your maths has to be perfect, and good practice can give you perfect maths. Now let's see the second example. Starting from rest, what will be Mahindra's velocity after 1 second if he is falling down due to the gravitational force of the Earth? So is starting from rest, so initial velocity, which is u, is equal to 0. Then force we have already found out in the last example, which is 733 newtons, the gravitational force on Mahindra. And then the mass of Mahindra, which is 75 kg, and we are told to find after 1 second the velocity of Mahindra after 1 second. So time is equal to 1 second. Then in order to find velocity, we can use this equation, the first equation of motion, which is v is equal to u plus at. We are having u, we are having t, but a we are not having. A we can find by using formula F equal to mass into acceleration. So acceleration will be force divided by mass. So force 733 newtons, mass of Mahindra is 75 kg. So answer we are getting as 9.77 meter per second square. So meter per second square I have written as, I have taken the seconds into numerator by and change the sign of the power. So meter second raised to negative 2. So division I have shown here, 733 divided by 75. We are getting it as 9.77 meter per second square, and then we can substitute this value for acceleration in this formula. V is equal to 0, the initial velocity, because Mahindra is on rest, and then the acceleration value 9.77, and time, which is 1 second. So answer is velocity equal to 9.77 meter per second. Meter per second is unit for velocity. Meter per second square is unit for acceleration. So this value which we are getting for velocity of Mahindra is much bigger than the velocity value which we had got for Mahindra in example 2 on page 6. That was of course because of a small mass, which was mass of Virat, and this value which we are getting is because of the gravitational pull from a huge mass of Earth. So this is 1.83 into 10 raised to 9 times Mahindra's velocity in example 2 on page 6, which was 5.34 into 10 raised to negative 9 meter per second. According to universal law of gravitation, every object attracts every other object towards itself with a definite force. That means when an apple falls onto the Earth's surface, Earth is attracting the apple towards itself. But also the apple attracts the Earth towards itself. But we never see that Earth is falling onto the apple. Apple always falls on the Earth. Earth never goes and falls on the apple. The reason is simple. It is the huge mass of the Earth which results in very negligible acceleration of the Earth. You can see here acceleration of the Earth, it depends on the mass of the Earth, which is 6 into 10 raised to 24 kg, which is of very high value. That means this high value is in the denominator. The value for this acceleration of Earth will be very negligible if we compare it with the apple. The apple will be around half kg, so it will be 0.5 kg. We'll get a certain value for acceleration of the apple, but if we compare that with the acceleration of the Earth, it will be quite higher. Acceleration of the Earth will be very negligible. We can take it as, we can consider it as 0, and that is why Earth do not go and fall on the apple, or it does not move towards the apple. Apple moves towards the Earth and it falls on the surface of the Earth. Next, The moon and the satellites revolve around the earth. They orbit around the earth because of the gravitational pull of the earth. But unlike Apple, they do not come and fall onto the earth. The reason is very simple. They are having their own velocities. Because of these velocities, they orbit the earth. And suppose if these velocities were zero, then definitely moon or the satellites would have directly landed on the earth. Now next, we have the earth's gravitational acceleration. The earth exerts gravitational force on every object which is near to it. And according to Newton's second law, whenever a force is exerted on an object, it results in its acceleration. So the gravitational force due to the earth on a body results in its acceleration. This is called acceleration due to gravity. So the acceleration which is caused due to the gravitational force of the earth is called acceleration due to gravity. So it is denoted by small g, and it is a vector quantity. That means it has magnitude as well as direction. Direction is pointed towards the center of the earth. So it is directed towards the center of the earth. Now next, there is a question asked on your textbook. The question is, what will happen if there is no gravity? The answer is very simple. If there is no gravity, there would have been no force of attraction between the particles. If there was no gravity, there would have been no gravitational attraction between any two particles, and hence no formation of the solar system or the galaxy would have taken place. It is the gravitational force of the heavenly bodies which is giving a proper shape to the universe or the solar system. So next question, if the value of capital G, which is universal gravitational constant, is double, then what will happen to the gravitational force or the acceleration due to gravity? So if it is double, then the gravitational force between any two particles will become double. The gravitational force will also become double, and hence the small g, which is acceleration due to gravity, will be also double. We are getting it through this formula. If this capital G, the universal gravitational constant, is made 2 times g, then definitely the force gets doubled. The gravitational force gets doubled, and because of that, the small g, which is acceleration due to gravity, is also double, because small g is gravitational force divided by mass. So here it will be 2 times f. So it will be twice the value for acceleration due to gravity. Now we'll see the value for acceleration due to gravity on the surface of the earth. We all know the formula for gravitational force, which is F is equal to G into m1 into m2 divided by d square. So m1 here we are taking as capital M, mass of the earth. m2 we are taking as small m, mass of the object placed on the surface of the earth. And then d square we are taking as r square, which is the distance of the object placed on the surface of the earth from the center of the earth. And by Newton's second law of motion, F is equal to mass into acceleration. So here it is acceleration due to gravity, which is denoted by small g. So F is equal to m into g. Number it 1 and 2, and then compare the equations. Compare 1 and 2. By comparing, we are getting as mg is equal to g capital M into small m divided by r square. So m and m cancels. Mass of the object cancels both the sides. So we are getting as g is equal to gm divided by r square. So r square we are replacing it by capital R, because it is the radius of the earth, the distance from the center of the earth to the surface of the earth. So it is capital R square. By substituting the values, 6.67 into 6, we'll get it as 40.02. We had done this in the last part. Then 6.4 square is equal to 40.96, and then value for this 10 raised to minus 11, 10 raised to 24 divided by 10 raised to 6 square, which will become 10 raised to 12, and after taking it in the numerator, it will be 10 raised to negative 12. So 10 raised to negative 12, 10 raised to multiply by 10 raised to negative 11, it will be 10 raised to negative 23. In 24 minus 23, it will be 1. So 10 raised to 1. Then multiply and divide by 100 to remove these decimals. And then you can multiply this 10 over here. So it will be, division will be like 40,020 divided by 4,096. You will get this value for that division. 9.77 meter per second square, which is the unit for acceleration due to gravity. So this is the value for acceleration due to gravity on the surface of the earth. Now here you can see that in this formula the value for acceleration due to gravity depends on two things. Now first thing, universal gravitational constant is that G, it is a constant. It depends on only mass of the earth and the distance between the object and the center of the earth. So it depends on the radius of the earth and on the mass of the earth. It does not depend on the mass of the object. So this is an important thing. So when you stand on two high places and suppose if you catch a stone, heavy stone on one side, and on one side you are catching a polythene bag, and suppose there is no air resistance, there is no friction due to the air is not blowing at all, and there is no buoyant force, no other force, only the force which is acting is gravitational pull of the earth, then both the object, the stone as well as the polythene bag, will travel with the same velocity. It will travel with the same velocity because acceleration due to gravity does not depend on the mass of the object. It depends only on the mass of the earth and the distance from the center of the earth. So next, what would be the value of G on the surface of the earth if its mass was twice as large and its radius half of what it is now? So we have to take this formula for this problem. G is equal to Gm divided by r square. What is given? If its mass was twice, so m is equal to 2 times m, and its radius is half of what it is now. So we have to substitute that G, so mass becomes twice and radius becomes, it is 1 right now, 1 r square, it becomes half r square. So what we will get for this? 2gm divided by 1 r square. So this 4 will go directly into the numerator, so it will be G is equal to 8 times Gm divided by r square. So the value of G on the surface of the earth if its mass was twice as large and its radius half of what it is now, then the value for G becomes 8 times its original value. Simple. It becomes 8 times its original value. Now we will see variation in value of acceleration due to gravity. So first, change along the surface of the earth. As you know, our earth is not exactly a sphere. It is not exactly spherical. Earth bulges out at the equator and it is flatter at the poles. So at the equator the radius will be more of earth and at the poles the radius will be shorter. So earth bulges at the equator and is flatter at the poles. Its radius is largest at the equator and is smallest at the poles. So if the radius is smallest at the pole, what will happen? If the radius is smallest, then value for G will be more. The same thing, G is equal to 9.832 meter per second square at the poles because radius is less, and G is equal to 9.78 meter per second square at the equator because radius is more. So denominator is more, value for acceleration due to gravity is less at the equator. Second, change with height. As you know, radius of earth is 6,400 kilometers, 6 into 10 raised to 6 meter. So if suppose an object is at a height like 10 kilometer above the earth's surface, it will be 6,410 kilometer over here. The distance will be measured as r plus h the whole square. The height, extra height will be only 10 kilometers. So it's not going to make much difference. 6,410 kilometer. It's not going to make much difference. But if the height is more, like of satellites and all, then it is going to make difference. The value of G, acceleration due to gravity, will reduce. So at the surface of the earth where height is 0, value for G is 9.8 meter per second square. So at the Mount Everest, which is 8.8 kilometer high, the value still remains same, 9.8 meter per second square. It does not vary. So maximum height reached by a balloon, man-made balloon, 36.6 kilometer. Value changes. It is the value for G reduces. It comes down to 9.77 meter per second square. Then the height reached by weather satellites is 400 kilometer. So value reduces to a greater extent, 8.7 meter per second square. And communication satellites, which are very high, 35,700 kilometer. So for that, the value for acceleration due to gravity is 0.225 meter per second square. So this is the height for communication satellite from the surface of the earth. So this has to be added with 6,400 kilometer, and then that will be the denominator, r square. So it is like r plus h, the whole square in the denominator. So that will give a smaller value for acceleration due to gravity. So this was the second factor where G varies, value for G varies. Third factor, change with depth. The value of distance r decreases, but m, which is mass of the earth contributing towards gravitational force, also decreases. Now you will think that as you go down, if you dig the ground, go down, value for acceleration due to gravity will increase. As you are going down and down, it will increase. No, it does not increase. Yes, of course, r decreases, radius of the earth decreases, but again the value for the mass which is contributing to this formula, which is mass of the earth, becomes less, because you are considering a center of mass. When you are going down, center of mass still remains to be the center, but your position is considered. Suppose this is the earth, this is the center of the earth, and by digging the ground you are reached here, then only this mass will be considered for finding out the value for acceleration due to gravity. Only this mass will be considered. So mass also decreases when you are going to a certain depth inside the earth. Mass also decreases, r also decreases, but as a combined value, G decreases. Value of acceleration due to gravity decreases when you are going to a certain depth. So the value of distance r decreases, but mass contributing towards gravitational force also decreases. Value of G decreases. So now there are two questions asked on your textbook. Will the direction of the gravitational force change when you are going to a certain depth inside the earth? Answer is no. When you are going to a certain depth inside the earth, center of mass still remains to be the center of the earth. So the gravitational force is still directed towards the center. So the direction does not change. It remains the same. Second question, what will be the value for G, acceleration due to gravity, at the center of the earth? So at the center of the earth, the mass considered for calculating the gravitational force will be 0. The mass considered will be 0. So if mass is 0, mass of the earth is 0 at the center of the earth, then value for acceleration due to gravity will be also 0. So acceleration due to gravity at the center of the earth is 0, because the mass used for calculating the gravitational force at the center is 0. Every planet and satellites have different masses and radii. The acceleration due to gravity depends on the mass and the radius of the planet or the satellites. Now if you compare moon's acceleration due to gravity to that of the earth, then acceleration due to gravity of moon is equal to 1/6 times that of the acceleration due to gravity of earth. So if you are jumping, if you are trying a high jump, you jump for 2 meters on earth, you will be able to jump 6 times higher on the moon surface with the same force, which is 12 meters on the moon surface. So hope you have understood whatever I have taught you in this fourth part of chapter Gravitation. Next part we'll be learning about what is mass, what is weight, and the difference between the two, and then we'll solve some few numericals, and then we'll see why we get high tides, low tides, and then we'll discuss something about gravitational waves. So thank you very much for watching this video. Please like, share and subscribe. Thank you very much.